Hello students, in this video we'll find the Schwarz-Christoffel transformation for the upper half space onto the upper half space with a small interval punched out. Let's consider the region, which is the complex plane, minus the interval 0, start at the origin, and go to IA. Okay, so go to I to a fixed number A, where here A is a real number. So A is a positive real number. Okay, so of course, what's this correspond to? This looks like the following, right? Looks like here's my complex plane. There's a real axis. And I want to map onto what? I want to map on, here's 0. I go all the way up to IA, like that. And I want the region, which is the complement, right? So I want to punch out this region over here. So there's my flow, my fluid, right? We're imagining there's a fluid here, right? Like so. And the question is how is fluid going to overcome this obstacle, right? So that's called an obstacle. Okay, how are the streamlines going to develop around that obstacle, right? It's an infinitely narrow, it's an infinitely thin obstacle, but it's there nonetheless, right? So you can think of this sort of like as a sequence of buoys, right? That's continuous, right, in some sense. And how is the fluid going to move around that sort of that impasse, or like a log, right? Think of like a log that's sort of wedged on one bank of the river. How is the water going to flow, or at least the surface water, flow around that log, right? Something similar to that. Okay, excellent. And so here's the scheme we're going to do. We're actually going to solve, what we're going to do is, this is a degenerate case. So this in some sense is a degenerate polygon. It doesn't look like a polygon, but it's a degenerate polygon. And here's how we're going to envision that. What we're going to do is we're going to do this. We're going to draw a line. There's the real line. There's negative epsilon. Then I'm going to go up over here to the point IA. I'm going to go down over here to epsilon. All the way over here, there's the real line, right? So what I'm going to do is I'm going to consider this auxiliary region, right? So here's my auxiliary region. Okay, this is R epsilon. Okay, that's R epsilon, and this is my region over here, R, right? So I want, as epsilon goes to 0, what's going to happen? As epsilon goes to 0, R epsilon converges to R as epsilon goes to 0, okay? So that's what we're going to think about. What we're going to do now is in this region we have a lot of different angles over here, right? So we're thinking about this only as epsilon goes to 0. So we're going to write down equations as epsilon goes to 0 and see what we get. Let's look at the alternate. So we have 3 vertices over here, right? Vertice 1, W1, W2, and W3, right? We're going to choose our points, choose z equals -1, z equals 0, and z equals 1 to map to W1, W2, and W3 respectively, right? So there we go. Now what are the exterior angles over here? The exterior angles, here's an exterior angle over there of alpha. Here's an exterior angle of beta. Here's an exterior angle of gamma. Those are my exterior angles I need to figure out for Schwarz-Christoffel, right? So what do I know? I know that alpha plus what? This is, as epsilon goes to 0, this is converging to pi over 2, right? So pi over 2, as epsilon goes to 0, is equal to pi, which forces alpha to be equal to pi over 2. Alpha is pi over 2. Great. All right, and then what's the beta going to? Well, beta, the exterior angle is going huge, right? The exterior angle is 2 pi. Beta is going to be equal to what? Beta is going to be equal to negative pi, which is going to be a positive exponent in Schwarz-Christoffel. And then gamma plus what? Same argument over here, pi over 2 in the limit, right? Is equal to pi, which forces gamma, the exterior angle, to be pi over 2. And of course, all these things are valid. These are all valid. So star is valid as epsilon approaches 0, okay? Good. So now we're in a great shape. What can we say? What we can say now is that our Schwarz-Christoffel mapping, f prime of z, is going to be what? It's going to be a, and then z plus 1 to the what power? To the -1/2. And then a z to what power? Then a z to the power 1. then is z minus 1 to the power negative 1/2, which is just going to be a times z over the square root of z squared minus 1. Great. We don't need any fancy calculus. It's a perfect antiderivative, right? This is a perfect antiderivative. I can try what f is, right? F of z is going to be a square root of z squared minus 1 plus b, okay? Now, of course, what happens over here? What happens over here when I plug in negative 1 to this formula, I'm going to get 0. So negative 1, what do I want to say? Yeah, so negative 1 is going to go to 0, and that forces b to be 0, right? F of negative 1 is going to 0. Similar to f of 1. F of 1 is going to 0 in the limit, right? Because really it's like f of net is like really negative epsilon, right? So it's going to be like negative epsilon. So we have to take a limit again, right? And then what's f of 0 going to be? F of 0. What am I doing over here? So I want to plug in 0. And 0 is going to ai, right? So f of 0 is I times a. And that's also equal to a times what? The square root of negative 1 is I. So that says that little a, that a capital is equal to a, right? Beautiful. Okay, and so therefore our function, f of z, the conformal map to this region, is going to be a, which is little a rather, so we'll put little a here. So little a, square root of z squared minus 1. And now let's find the streamlines, right? Where the streamlines are going to be a square root of t plus ic squared minus 1, right? Where t goes between negative infinity, and c is a constant. So here c is a constant. So now we have our streamlines. Our streamlines look like this. The closer they get, the more quickly they go over, right? So here are our streamlines. You get farther away, you go further up like that. So that's how you avoid this obstacle over here. So in other words, the water that's getting very, very close to the base of the log on the shore gets very, very close to the base of the log, hits the log and starts to go up and then back around, right? The ones that are very far away from the log just basically keep going straight, right? And you get closer and closer and farther away from the shore, you still are affected by that log in the stream, right? But it has less and less of an effect as you keep going, right? So as you keep going, the effect lessens, right? As you get farther and farther and farther away from the obstacle. But as we see, of course, here, that A plays an essential role. The length over there is the longer the length gets, the more bend you get, right? So as I increase A, the points close to the boundary increase naturally in length exactly as linear growth as we would expect to see in that factor. So this is one of the few examples of a Schwarz-Christoffel transformation where the integration actually becomes very, very simple, right? So this is this obstacle problem, this degenerate polygon yields a very, very simple thing. For other sort of degenerate regions, double slits and things like this, it gets a little more complicated, but this is a good example of a single obstacle moving a flow, an incompressible, irrotational flow around an obstacle. Thank you very much.